Hello class, today we're going to talk about polar bonds and molecules. This is chapter 8.4 in your textbook. So today's learning objectives are being able to use electronegativity to identify polar versus nonpolar covalent bonds. Then you must be able to draw correct dipoles on a covalent bond. And finally, you'll need to look at these dipoles or vectors and add them up and then draw a correct net dipole on a molecular compound. Looking at these learning objectives, it's pretty clear we'll have to revisit electronegativity, and then I will have to identify the difference between polar and nonpolar covalent bonds. Finally, I'll have to define the term dipole, and then, of course, the term net dipole to you. So you should recall that electronegativity increases as we go up a period, as you go up a group and across a period, leaving fluorine to be the most electronegative element and francium to be one of the least electronegative elements. So, keeping that in mind, let's look at some differences in electronegativity. So, for instance, if you have two atoms and their difference between the two and they're bonded is between 1.7 and 4.0 on the electronegativity scale, that would be an ionic bond. If the difference is 0.3 to 1.7, we'll identify that as a polar covalent bond. And finally, if it's 0 to 0.3 difference, generally we consider this to be a non-polar covalent bond. Now it turns out that these terms between polar and non-polar covalent can sometimes get hard to discern. For instance, one of the most common bonds is the CH bond, a hydrocarbon bond. It's an organic chemistry, kind of a classic bond. If you were to look up the electronegativity of carbon, you would see that it's 2.5. If you looked up the electronegativity, you would see it's 2.1 for hydrogen, leaving a difference of 0.4 in electronegativity units, which would tend to put it in this region here. However, almost all practicing chemists consider a CH bond to be non-polar covalent. So for the most part, once this number starts getting pretty low, we consider it non-polar covalent. If this number is in the region of around 1, we consider it to be a polar covalent bond. Now what I've shown here next is to sort of give you an idea of how the electron density is positioned around molecules depending on whether they're an ionic, polar covalent, or non-polar covalent bond. So in the first structure, what you see is that the electron density amongst on the non-polar covalent bond is evenly distributed. Okay? So as you look at this structure, you see there's as much electron density all the way around it. So in other words, the electrons that are being shared in the bond are equally distributed about the two atoms, and we consider that to be a non-polar covalent bond. In the case of the polar covalent bond right here, what we see is that even though these two nonmetals, and they would be two nonmetals, are sharing electrons, they're not sharing very evenly. It's hard to see, but there's symbols on each side. One says delta minus, and one says delta plus. The delta minus means that there's a greater amount of electron density on what must be the more electronegative element, and there's less electron density, delta plus, on the atom that has a smaller electronegativity. Okay? And finally, we have the ionic bond. Okay? That's right down here. And we see that all of the electron density, for the most part, is on the anion, and then we are stuck with the cation, and they're simply bonded together by electrostatic forces. Opposites attract, and that is an ionic bond. So that kind of gives you a feel for the difference. Probably the most important is for chemists, the most important bond that they deal with the most is this polar covalent bond. Okay, so a classic example here would be OH. Okay? OH is the alcohol functionality, It has oxygen is much more electronegative than hydrogen, and so oxygen, so what happens is there's a lot of chemistry that can go on here because of the polarizability of the electrons. Now again, what I've included here is an electronegativity scale to sort of give you an idea of the electronegativity differences. And again, you see that for the most part, where the greatest electronegativity focus tends to be in what I call this, northeastern corner of the periodic table, which is where the nonmetals are. So this is where a lot of interesting chemistry takes place, and you start to see that when you couple this with hydrogen over here, you get to see some nice electronegativity differences. Now here I just basically have a very simple picture of showing a polar covalent versus a nonpolar covalent bond. So if you look at chlorine, Cl2, you see that this picture shows that the electron density is pretty much equally distributed about the two chlorines. Why? Because chlorines both have an electronegativity of 3, and so there's really no reason for the electrons to go to one chlorine or the other. And so this molecule, oops, let me go back there. This molecule is Cl2, and when we look at it, it only has one bond between it, right? Chlorine, chlorine. And it has just one bond, and that's a nonpolar covalent bond. Sometimes we use the terminology NPC, so it's a nonpolar covalent bond. And so we would say chlorine, Cl2, is basically a nonpolar molecule. Okay? So it's a nonpolar molecule. Okay, chlorine. Now if we go down below and look at hydrochloric acid, there's a much different situation. Chlorine has electronegativity of 3, but hydrogen only has 2.1, so that's a difference of 0.9. This is definitely a very strong polar bond between the two. As you can see, most of the green, or the electron density, is sitting on the chlorine. Very little is on the hydrogen. So we put the delta minus towards the chlorine, the delta plus towards the hydrogen. There's only one bond between hydrogen and chloride in HCl. This is a polar bond, and so when we would actually talk about HCl, we would say it's a polar molecule. Okay? Polar molecule. Today in your homework, you'll have to be able to make that distinction between a nonpolar and a polar molecule. Now moving on, I've just simply showed you a computer generated. This is actually generated by something called ab initio calculations. It means a supercomputer has actually calculated the electron density on something like an OH or an alcohol. The gray material happens to be electron density, and again you can see that oxygen has, is again a 3.5, hydrogen's 2.1 in terms of electronegativity. So much of the electron density is on the oxygen, and we say delta minus, delta plus. Here's an example of another computer-generated image. This is F2, or fluorine gas, and you can actually see experimentally that the electrons are being shared pretty much evenly by the F2 molecule, much in the same way that chlorine was. So again, F2 would be a nonpolar molecule, and if there was some kind of another atom attached, let's say a carbon, and this structure was to go on to make some type of structure, no matter what now, because we have this one OH bond in the molecule that's polar, we would say this molecule would be a polar molecule. Okay. Now we're going to shift gears and do something where it's called drawing bond dipoles, and what I have here is the molecule boron trifluoride, BF3. If you were to go back and look at your electronegativity chart, you'd see that boron is not very electronegative. Fluorine, of course, is the most electronegative. And so on the left-hand side here you have the Lewis structure. And on the right-hand side, what we've done is we've drawn bond dipoles between the boron and the fluorines. The way these bond dipoles work, and I'm going to make new arrows that are a little bit bigger. Okay, so I'll draw them there. The way these dipoles work is that essentially you draw them from the less electronegative element, or the delta plus. This is delta plus, this is delta minus. You draw from the delta plus to the delta minus. So I'll draw a bigger one here. Here's a bond dipole. Okay, and just because it's simply an arrow, and of course arrows can be reactions in chemistry, so we want to make sure everybody knows it's a bond dipole, and so we put this little horizontal line through it so people see that. And it turns out that we could do this for every time we have a delta plus and delta minus. So we also have one on the other fluorine, so we'll go ahead and draw that, and we also have one on the other fluorine. So we actually have 3 different bond dipoles, or vectors, okay, or vectors. Okay, and so we've drawn them like this. So that would be a bond dipole. It's simply, a bond dipole is simply an arrow that's going from less electron density to more electron density. So here is another example, probably a more relevant example. This is methanol, CH3OH. Remember, we kind of made this postulation that carbons and hydrogens, these bonds are NPC, are nonpolar covalent. So basically we won't draw any bond dipoles down here. However, oxygen is clearly much more electronegative than hydrogen and carbon. And so if we were to draw bond dipoles, we would draw one like this and one like this, going from both of these atoms towards the oxygen. And again, we should put the little arrows so that you can see them. And finally, we would then, of course, might want to label this delta plus. This whole area down here is a delta plus. And essentially what you start to see is that, in a way, we're starting to build up lots of electron density. We see delta minus, you might even delta minus. So we're going to get a lot of electron density on the oxygen. Okay? And that's what's sort of shown over here. Okay, partial charge notation. So again, this is just a way so that you can kind of start to get a feel for like where the electrons are. And of course you say, well, why do we care where the electrons are? Remember, electrons are where chemistry occurs, and that's why we do this. So now let's talk a little bit about the net dipole of molecules. And before we do that, we better start defining a few terms. And so the first term, let's just go ahead and give you a formal definition. I've said it already, but sometimes it's hard to pick up on it. So here is the formal definition for a dipole. It's a separation of charges within a molecule between 2 covalently bonded atoms. So the atoms have to be next to each other. So I'll give you about 20 seconds to copy that down. Okay, so that's the definition for a dipole. Now let's talk about the definition of the net dipole. Net dipole is when you take all these dipole vectors and you sum them up to give one overall dipole. So in other words, you're adding up all the arrows that we were drawing in some of these molecules. Remember, some of these molecules had 3 arrows for each bond, and now we're going to actually add them together and make one overall dipole. Okay? And so here's a couple of examples. Okay, one is CO2, and you see it says it has no net dipole moment. And so you might ask yourself, well, how could that be? Because after all, if you were to look at this molecule, you could look at the carbon in the middle, carbon dioxide in the middle, and you could say, oh, well, oxygen is more electronegative than carbon, so I'm going to draw a vector that way. Okay. And I'll make sure I know my dipole. So here's one dipole, and you go, well, you know, There's another one going this way. Okay. So it seems that like you've got two vectors, you've got two polar covalent bonds, but the issue here is you sort of have a tug of war going on, and both of them are pulling at the same amount of electrons away from the carbon with the same in opposite directions with the same amount of intensity. And so essentially what you get is the molecule sees no really difference, or it's sort of like, imagine it being a tug of war where the flag doesn't move, and you'd think even though everything's going on and people are grunting and sweating, nothing's happening. And that's basically what happens with this. You would say it has no net dipole moment. However, if we were to look over to the water molecule, it's a much different story. Again, oxygen is very electronegative, so we'll draw our dipole there, and of course from the other hydrogen as well. So we have two dipoles. Now what happens is those two dipoles, when they add up, turns out that together we sort of have one net dipole that's going straight up. Oops. Straight up. Okay? Now that might be a little bit hard to see, but if you were to add these two vectors, they would add together like this. In fact, when you add vectors correctly, the new line that's drawn should actually also, the length of the line determines the intensity. So the length of this line should actually be about double if you added those two other lines up together. So something like this, okay, would be the net dipole. And if they just wanted the net dipole, then you would kind of get rid of the ones that you just added, and you would sort of have like this picture off to the right. Now this picture to the right has a number, and you can calculate numbers. We're not going to actually do any calculations. So what this basically says is that if you were to actually really look at oxygen in a more generic fashion, it has a negative sort of charge on that side, and on the bottom side it kind of has a plus charge between the two hydrogens, and that kind of makes water act like a little battery. Okay? Now, so I know this adding of vectors is a little kind of maybe strange to some of you, so what I want to do is just show you a little drawing to give you some kind of perspective. So let's say the one that I like to do is, I'm from Minnesota. I like lakes and rivers. We have lots of them there, a lot more than we actually have in California. So I'm going to draw a river. Here's my water. Okay. So there's my water. And quite often in Minnesota we go to a place called the Boundary Waters Canoe Area, and we like to take our canoes. I actually have my own canoe. And so here's my canoe. Oh, I shouldn't do that. You know what? My canoe is actually green. It's made by Winona. So I have a green canoe, and let's see, my canoe is kind of a greenish blue actually, so it's kind of like that color is probably better. So there's my canoe, there's me, and my dog. That's my dog Yogi, and we're in our canoe and we're gonna go across. Now of course, usually when we cross the river, what we want to do is we just want to go straight across. Okay? So straight across. So let's assume I started here at X and I just want to get to X. Okay? But unfortunately, there might be something else going on. The other thing that's going on is that the river has a current. And let's say the current's like that. Okay? Is going that direction. Maybe better to draw it on the side. The current is moving that direction and maybe that strength. So I think all of you understand that if I try to go straight across this arrow that's facing upward, that I'm not going to end up where the X is, but that I'm going to end up, someplace down here. Okay? And not quite where I wanted to go because of the current, as long as I was trying to go straight. And this is the basic idea on how you add these vectors up on the molecules. So on the molecule then, these would be I'll label them, but these would be the bond dipoles, this one and this one, okay? And then this guy right here would be the net dipole. Kind of where did I end up? So I hope that helps a little bit in trying to figure out how to add these vectors, if you will. So now let's practice, okay? And so I have a few ones for you to try. So go ahead and get out your whiteboards. If you're not in room 710, then you'll have to do this on a sheet of paper, okay? And make sure at the end of class you put the whiteboards away. Okay? So what you're going to do is show the polar bonds, delta minus and delta plus, and then you're going to predict the net dipole moment of the molecule. You'll need to use your electronegativity chart, which is on page 177 of your textbook if you're not sure about the electronegativities. Of course, for many of them, you can just look and know your periodic trends from chapter 6, and you shouldn't have a problem figuring out which which of the elements is more electronegative. And now remember, let me draw this right now. Don't worry about CH bonds. CH bonds are not polar covalent, so you won't have to deal with them. So here are the four that I want you to try. One is phosphorus trifluoride. By now you should know that this is trigonal pyramidal. Trigonal pyramidal. And then also you have ammonia, which is, believe it or not, trigonal pyramidal. And then you have carbon tetrachloride, which is tetrahedral. I'll just say tetra. And then you actually have bromine pentafluoride, which is a bit different. And I'll leave this up here. It actually has a square pyramid shape. So it has four fluorines in the plane of the bromide and then one above. Okay? So I'm going to stop the presentation right here, and if the substitute can just keep this, can also just pause the video right here, and you guys can use this and work these problems. When you're done with this, there's a homework assignment, a homework sheet that will be handed out to you. Hope you have a great day.